We have noticed historically that most students tend to be more comfortable with exponential functions rather than logarithms, and so we're going to spend a little bit of time reviewing logarithms and their properties in the next few pages. In particular, we're going to start with really the definition of the logarithm, and that's the idea that the logarithm somehow inverts, or is an inverse function of the exponential. If we have a to some power c gives us x, that's turning an exponent into a value. We can take that value, use it as the input for log, and get the exponent back. In particular, if we consider an example like log base a of a to the 7, let's let x equal a to the 7. And what we have then is a statement about this. We're asked to calculate log base a of a to the 7. So let's say that c is log base a of x, or we could also say that's back to our original statement of a to the 7. How does that help us? Well, that's the same thing as saying a to the c is equal to a to the x. A to the c is equal to x itself, rather. So this statement here is the same as this statement here. That's the equivalency, but we already know what x is. X is a to the 7. And so right away, we can see, well, the only way that's going to work out, the only possible solution is that c equals 7, but what's c? C is log base a of x. What's x? A to the 7. So this whole expression up top here is what we're looking for, a to the 7. That must equal 7 as well. And this is one of the ideas you get about logarithms when you're learning them. First is that logs somehow output exponents. So here we see common base a and the output of the logarithm of a to the 7 is just the exponent itself, the 7 value. Notice what we did here is we nested log and exponentials. Here we're going to nest those two functions again, one inside the other, but the exponential is going to be on the outside. And what we can do here is focus on the log base a of 25. So some of you might have a good guess as to what this is going to be already, but let's just go through the calculations. So what we're going to do is let log base a of 25 equal c. And that's the same thing then as saying a to the c is equal to 25. From there, it almost seems trivial. We have this statement here that we've got a to the c equals x. Well, c is log base a of 25. And we get right back to our 25. So again, more through an inverse relationship, or it's sometimes easier to see as an inverse relationship. If we start with 25, take the log, then use that as an exponent, we get back to the value we started with. So this inverse relationship is what's manifested through these two equivalent relations here. So recall that log and exponentials are inverse functions. Okay. Now it's pretty rare, quite frankly, to see simple expressions like this where we have the same base and some power and they just end up canceling out. Let's take a look a bit further. Let's take an example like log base 10, very common in the sciences, of these various different values. Well, let's say our unknown value for the first one is log base 10 of 10,000. That's going to be equivalent to the statement that 10 to the x is going to equal the value inside here. Pardon me, a little extra one there. So is equal to 10,000. And if that's the case, well, we can pretty clearly see that that's 10 to the 3, 10 to the 4. And so x must equal 4. So log of 10,000 base 10 is simply going to equal 4. Similarly, if we look at log base 10 of 1 over 100, if we let that equal x, then that's the same thing under our equivalence with exponentials as saying 10 to the x is equal to 1 over 100, but 1 over 100 can be rewritten as simply 10 to the negative 2, and so x must be equal to -2. And so we get log base 10 of 100th, 1 over 100, is going to be -2. And again, once you get the familiarity with this, you see you can put it in short form. What exponent is this base 10? Oh, it's 10 to the -2. Okay, so the answer of the log, or the value of the log, is -2. And so we get some of the simpler relationships that we've seen before in those first examples. The inverse relationships, we formalize them here. More typically, the relationships that we're going to use are essentially the log rules. These log rules can be derived from these kinds of relationships, but it's a bit tedious. We won't go through it here. We're simply going to take these as rules that we can use during the course. The first, of course, is a multiplication of interior pieces can be transformed into sums. Multiplication inside logs translates to a sum outside. So log of a times b turns into log of a plus log of b. And of course, if we're multiplying turns into addition, division will turn into subtraction. And last but not least, if you think of repeating the multiplication rule over and over and over again, so say we had log of a times a times a, or a cubed, we'd end up with 3 times log of a, and we can encapsulate that in even more general form with this power rule. Powers inside the log can become multipliers or scaling outside. There we go. So we can bring the, or sometimes we'll say bring the power down front. So those are just ways to try to remember these common rules and try to remember that it's the log of the multiplication that leads to the addition. One of the classic traps is to mistake and say log of a plus b is a multiplication outside. Again, try it with some test values as a way to remind yourself in the middle of an exam or a test of what is actually correct and what's not correct, or simply memorize log is special and log of multiplication, because we're talking about exponents, turns into addition of exponents. That's another way to tie it back to the log and exponential relationship.